1 lesson 37 is going to have us add and subtract whole numbers with decimal numbers, and squares not the shape but the operation, and that's what's called square roots. Maybe something new. Something that's not new and probably familiar is seeing a sign maybe like this one advertising something at a store as $3 each. Ever notice that it's writing it, this way instead of the way we've been using in the math books, right? Just a dollar sign and the number. We see that the dollar amounts with or without a decimal makes sense. You can write it either way. We can write whole numbers with or without that because those zeros we only really show in money. Otherwise, they don't have a value. They're just placeholders showing us right where the zeros, where the cents would be. So all of these mean 3, and they're all correct, but this is probably the way you would typically show 3. As we see in the following examples, it may be helpful to write a whole number with a decimal point when adding and subtracting. So adding the decimal, kind of like this one in some cases, might not be a bad idea. Let's take a look. Paper used in school is often 11 by 8.5, 11 inches long, 8.5 inches wide. That's what your filler paper is, all your handouts. That's the dimensions, the length and width of sheets of paper at school. Find the perimeter by adding, of course, lengths of the 4 sides. Well, not all the sides are the same, and not all the sides use the same place values. We've got 11, the whole number. We've also got 8.5 over here, which has a tenths place, a decimal. So when you add numbers that are decimals, you remember we line up the decimal numbers. If we've got whole numbers in there too, this one doesn't actually have anything, but it wouldn't hurt to put a decimal and maybe even show the zeros, just to make sure that we understand where everything should line up and that we don't. You see what would be wrong if we went like this? And we did this, and we added that. We've got the place values out of whack, and by putting this decimal, we can see right there that this is diagonal and all that's wrong. And then we add 5 plus nothing, or 0. They've kind of got this written funny where we have to add 5 twice. So they add the 5 down here to this, I guess. I would probably show it as 11 plus 8.5. Oop, I almost did it right there. 11 plus 8.5. And let's just do it all in one. 11 plus 8.5. So these are the lengths, these are the widths, and you can add them all together. And I like showing a 0 here as a filler. It's not worth anything, but it's a nice placeholder, right? Then you go, right, up and about 10, 19, 3, 39. Don't forget to drop that decimal down straight down. So they just show it with an extra line here. I don't like that very much. So that is how we add when we've got a mix of whole numbers and decimals. You do the same thing with subtraction. 12 and 3/4 or 75 hundredths. Subtracting 5. I don't know why this looks like a times sign. That looks like a mistake to me. Watch out in your book if it looks like that. It should be showing it like this. You subtract those, maybe put a decimal after that 5. Maybe even add zeros. So you've got everything filled. And you're feeling comfortable then. 5 plus 0, 7 plus 0, 12 plus 5. Or sorry, 5 minus 0, 7 minus 0, 12 minus 5. And it all matches up nicely. Recall that we find the area of a square by multiplying the length of a side of the square by itself. So to find the area of a square, you've got 5 times 5. That number is always the same because sides are all the same. So I guess I lied a little bit. We are talking about the shape of a square a little bit, but I don't usually think about, how squares relate to squares and square roots. But it's a good way to remember that each side being 5 means area is always a square of its sides in a square. And the sides are the square root of the area in a square. 25 square root is 5. Why is that? Because 5 times itself one time is 25. Another way to show that is 5 squared. We do that with an elevated small 2. That means times itself once. 5 times 5. When I'm multiplying, that's how many times it's a factor. 1, 2 times. So I use that 2 as what's called an exponent right here. The 2 is an exponent. And literally, I read this as 5 squared and then equals 25. Let's try it again. How do I show 3 squared? 3 with a little 2. What is 3 squared? Well, it's 3 being used as a factor 1, 2 times, which is 9. You can do that with any, right? Any number. What is 12 squared before I scroll down? That one you might need a calculator at this point yet. But that's how I show it, a little 2 up there. Sometimes in a calculator you have to type 12 and then you type like a caret and then you type the exponent you want to use. And this or this, it's all going to come out to 144. And then if I reversed that, the square root of 144 is going to be, guess what? 12. It's like the opposite. It's the inverse version of what I just did with the squares. So this should say 144. And then if they say, why don't you add 3 squared plus 4 squared? Let's just find 3 squared, which is 9. Oops, fakes. 3 squared is 9. 4 squared is 16, right? 4 times 4. So 9 plus 16 is 25. The step that's not shown in B is the 3 times 3 and the 4 times 4. But you might be able to do that in your head with your times tables. That's why they're so important, so you don't have to write all that out. We can use an exponent of 2 with the unit of length to indicate square units, like square centimeters instead of SQ period or square. We could just say cm with a little 2, centimeters squared. What's the area of a square with sides that are 5 meters? We said that's 25 meters squared. And then there's this square root sign that looks kind of like a check mark. And what that basically does is it undoes the squaring we just did. It doesn't show it, but you can think of a little 2 here maybe. So what times itself once is going to be 100? What times itself, as a factor twice will be 100? What times itself will be 100? 10, right? Is 100. So the square root is 10. Perfect square means it's got a whole number square root, and everything we've used so far is an example. Perfect square would be 25. A perfect square would be 100. Perfect square would be 49. Because 7 times 7, 10 times 10, 5 times 5, 5, 7, 10, those are whole numbers. I don't have to use a 3.6 or something like that. That would not, be a perfect square. We don't use those very often in our books. 3 and 6 tenths times 3 and 6 tenths is hardly perfect. And you can count up first, second, third, fourth perfect square by going, 1, 2, 3, 4. So the fifth perfect square would be 25. You can think of it by its units, length and width, if you'd like. So that's squares and square roots, and earlier we had decimal adding with whole numbers. Why don't you pick 2 from each section of new things, 2 of these and 2 of these, and we should be good to go. Make sure you get those right. Do your very best.